Hi there, we're going to take a minute and discuss linear regression. This is the second half of chapter 4 in our class, and we'll give it a few minutes and talk about it. So I want to start this part with a research question, and it says here, how much alcohol can one consume before one's blood alcohol content is above the legal limit? So this is a research question, actually, that it was an undergraduate statistics project from some students at the Ohio State University. And they explored the relationship between blood alcohol content and other factors, such as the amount of alcohol consumed, gender, weight, and age. So here's the data. They had, I believe, 16 participants. I'll have to count this later, but around 16 participants in this little study they designed. And when the volunteers showed up, they were randomly assigned a set number of drinks to have. And you can see that here. So you can imagine they put put all these different quantities that they needed consumed. They put them in a hat. The students came in, randomly drew a number from the hat, and they were assigned to drink that number. So you can see here, as mentioned before, there's gender, weight, the number of beers, the blood alcohol content, first sober and second sober. So this study was one where they did a little more sophisticated analysis than just simple linear regression. We're going to take just 2 of these columns rather than working with many of them, but I just wanted you to have the whole data set to see it. Basically, first sober was the police, public safety conducted a blood sobriety test prior to their consumption, and this was their score, and then after their consumption, so you have an idea of what all the variables mean. So this was the data that I want to look at with you, which is basically the number of beers on the x-axis. That's going to be our explanatory variable, and the blood alcohol content on the y-axis, and that's our response variable. If you want to pull this up yourselves, you can look in StatCrunch and go to Explore Data. And if you type in this into the search engine, the data set should be right in front of you. That is just what I call the data set and then my name, and that way you don't have to look at a lot of different data sets and sift through. So if we look at this scatter plot, we can see there that there is a slight trend here. We can see as participants drank more and more beers, and then were given a breathalyzer, the blood alcohol content increased. And I don't think that's surprising for anyone, but you can see that. And I would say that this looks a lot like, the trend looks very linear to me. I could take a straight line and fit the data, and it would do a good job summarizing this relationship between our explanatory variable and our response variable. So here's a line. This is our line of best fit. We're going to call it a regression line. Your algebra teacher would have called it a line of best fit. They're the same thing. And you can see here that this line is doing a reasonable job summarizing this relationship. So how does this line come to us? Well, I want to talk to you about how the computer program does this. We're not going to compute the line ourselves. We're going to rely on technology, but it's important for us to know how the line came about. So basically, the line came about because of things called residuals. And I kind of think of residuals as errors. So as you can see here, I pointed out a few residuals. The red dot is an actual value in our data set. I'll call it an observation. This is that individual that drank 9 beers and had a pretty high blood alcohol content there. And that was what we actually observed. The line of best fit, or the regression line, would have predicted their blood alcohol content to be much lower. So this distance we observe between the observed value and the line is what we call a residual, or an error. And likewise, here's another one. You have this person here who drank 8 beers, and you can see that there is a difference between what they consumed and the blood alcohol content, and then what the line. So the line would have overestimated it here. So the model's not going to be perfect. It's not going to go through every single dot that we have. Let me flip back here, and also I want you to see that there's variability. See, there's 5 for this number of beers, 5. There's a lot of variability in what their blood alcohol content is. All these individuals drank the same amount of beer, but their blood alcohol content was quite different. And you can see that here with these repeated values over different numbers. So again, we recognize that the line of best fit won't hit every single dot in our data set, but it's doing a good job summarizing it and getting as close as possible. So here's our official definition of residual. I like to say in spoken word, I call it observed minus predicted. Or as a formula, we say it's y minus y with a little caret on top, which you'll hear me speak as y hat. That's our predicted value. That's the level of blood alcohol content that the blue line would have predicted. So if we think about that, let's compute a few residuals informally right now. So a positive residual means that the predicted value is too small. So you can see here our prediction here for 9 beers is too small. It's an underestimate of blood alcohol content. So this is what I mean. I'm using a horizontal line here to help me match up with my axis here. So it looks like it's approximately 0.15 if we're going to be generous here. So that was the predicted. But the actual, if you go back and look at the data, the actual blood alcohol content was 0.19. So if we take the observed in red to correspond with the red dot and subtract the predicted in blue to correspond with our blue regression line, then you can see it was off by about 0.04. We call that a residual. Likewise, let me do another one. A negative residual means that the predicted value is too big, so it's overestimating blood alcohol content. So again, I'm going to use another horizontal line here. Looks like that is, and I'm going to have to use my best guess, about 0.13 here as a prediction. And if I subtract off, that's the blue, I subtract that off from what we observed, and I can go back and look at the data that is a blood alcohol content of 0.12, then you can see it is a negative residual. So these residuals, these observed distances that the dots are from the actual regression line, some are quite close and some are far away, they're what we take into account when we want to find a line of best fit. So there is an algorithmic process that the computer goes through trying to find the line that gets as close as possible to all the dots simultaneously, and every time there is a calculation of the residuals. Now, the trouble with residuals is much like we had with the standard deviation. With some of them being positive and negative, they'll cancel each other out, and some to zero often, or close to zero. So we have to square the residuals so that they don't cancel one another out, forcing all the numbers positive, and then in a simplistic way, the computer adds up all the squared residuals to find out which one produces the smallest sum. So again, a series of different lines are checked to see which one fits the data. The choice of the best fit is the one that has the smallest sum of squared residuals. So they're trying to find the smallest distances in respect from the dots to the line. Now, there are as many residuals in your data set as there are paired observations or bivariate data. So in this case, I believe there were 16 students. They would have 16 residuals, because I can literally, or the computer does, computes all of these distances from the dots to the line. Now I know that's a lot of explanation, but I really want you to understand where this line of best fit comes from. Now once we have the line of best fit, and you know, a line, we can recall from your algebra class, is y equals mx plus b, where m is our slope and b is the y-intercept. Well, in statistics, it's the same concept. We just label some of these features a little differently. So we put a little hat, as I mentioned, or a caret on top of the y, so that we know that it is a prediction, not an observation. And they reverse the order here. Notice the x is mentioned last, so the coefficient on x, which is b1, is our slope. And this value here, b sub 0 or b0, is our y-intercept. So the one next to x as the coefficient is slope, and the other b is our y-intercept, the one isolated. It's just a constant. So again, they reverse the order. For some odd reason, they like to use b twice rather than just once, so they give it subscripts to denote one from the other. Now, as I mentioned, these are very lengthy and complicated formulas to do, so we're going to use StatCrunch to calculate the line of best fit for us, and I'm going to demonstrate that now. So if you log into StatCrunch, you can see here you're going to hit Explore, Data, and then you can type in BAC space MGOR. And that brings up our classroom example. Oops, don't click on my name, click on the actual data set. So here's the data we mentioned before. Yes, there are 16 students. I just double checked here. And we are going to go through the process for me of showing you how to do this. So we're going to hit Stat, Regression, Simple Linear. Now once we get into this, all we have to tell StatCrunch is who's our explanatory variable, thus on the x-axis, and who or which of our variables is our response variable, which will be on the y. And as you've noticed in a couple of my displays, I have put beers in as the explanatory variable and blood alcohol content as the response variable. So you just have to tell it which one's which and hit compute. So we get a lot of output here, more output than we possibly could need. Most of what we need is up here in this first section. So it reminds you that the simple linear regression results. And the fourth line down, which I'm highlighting now, is our actual line of best fit. It is our linear regression results. So here we have it there. Lots of decimals here. We'll round this a bit when I write it down in a minute. But that is it. Notice BAC is that's what I called our Y variable, so it's going to give it the title that I titled it in StatCrunch. And of course for the number of beers, I just called that beers. Another thing to mention is there's R, the correlation coefficients, another 2 lines down. So what we suspected to be a pretty strong positive correlation we do have here at 0.89. And lastly, this is one of 2 pages. So if you click on this arrow, you can see the actual sort of reverse from me. I had red dots and a blue line earlier, but you can see the data with the regression line. And again, if you let your mouse hover over that, you get the line there as well, using Y and X. On the first page, it's going to use more of the column headers that you use. So that's how you can find a linear regression line. Pretty simple. So here I decided to round to 4 decimal places, and with Y and X, as I mentioned before, here is our linear regression line. This is the same one except that I used the names of my columns, which was beers and BAC for blood alcohol content. I also put a little hat on top of it, since I want to recognize that this is a predicted value. So that is a predicted value, as I mentioned. That's why we often generate these, is to make predictions. So we can predict one's blood alcohol content, according to this data, for somebody who's consumed 8 beers. Now, I arbitrarily chose 8. Thought that would just be interesting. You could choose 7.5, 2 1/4, 1 beer, whatever you'd like, but we can now use this regression line to make that prediction. Let me show you how that works. So if you notice, I took my equation and I inserted in place of beers 8. Now I'm going to follow the order of operations and do the multiplication first. and then I'll combine that with the negative 0.0127. And the predicted blood alcohol content for an individual who drinks 8 beers according to this data would be 0.1313. So that is a nice way to use our regression line, is to simply make predictions. So here's a nice visual of our results, if you're a visual person. So again, we wanted to make a prediction for 8 beers consumed. So on my graph, we'll take the 8 beers and I'll sort of track up to the line, and that's the predicted value. And if I use a horizontal line there, you can see that I can't tell exactly because this vertical axis isn't detailed enough, but you can see that a value of 0.1313 is a reasonable number. And that's what we're doing when we're making predictions. We're using this line that summarizes this relationship to predict the response variable.